Okay, we can begin. My name is Bruce Director. This is the fourth and final part of this four-part series on LaRouche's economics. There will undoubtedly be more classes on LaRouche's economics in the future, but this is the fourth in this series. And in the first three parts, if you joined us for those, we spent a lot of time discussing the essence of LaRouche's economics and showed definitively that the science of physical economy as LaRouche developed it basically contradicts a lot of the assumptions and axioms that not only dominate science today, but also are causing a lot of confusion in the general population on the question of policy and economics. And so if you haven't seen those, if you weren't participating in them, or you missed one or two, you can find the recordings of those on our website. But in brief, what we showed in those classes is that LaRouche place the emphasis on human creativity as the substance of the economy. So if you're going to understand how the economy works and what economic policy must be, you have to turn your attention to what is creativity, as LaRouche often called it, what creativity per se. Tonight we have Tony Pappert again with us, and I want to start off by asking him a question, because when you pose the question of what is creativity and creativity per se, how it actually manifests itself in the economy, it's integrally tied up with the question of what is science. And Tony has some important things to say about what LaRouche had to say about what really is science, which will probably shock many of you, because it's not generally what people think of science or what is taught in the schools. So Tony, why don't you come in here? And we were discussing this in several discussions and in readings of LaRouche's writings that we have been doing over the recent period. And you have honed in on a crucial question of what is science that I think is the relevant point to start our discussion tonight.
Yeah, we began the series with LaRouche's struggle in 1948, beginning in 1948, against artificial intelligence and the cult of artificial intelligence, what's become the cult of artificial intelligence. And now I think we can begin the last class in the series with the debunking of the cult that science is mathematics, which is pretty much universal. A mathematical description of nature. I mean, this is not only going on in hard science fields, but I mean, as I think everybody knows, you have numerous master's candidates and PhD candidates who are fitting various human survey results and other things into mathematical schemes to produce scientific-looking papers about subjects like sociology and anthropology, nothing but a bunch of mathematics, which is all phony. I mean, this was one of the first discussions I had with Lyndon LaRouche soon after I met him, I believe in 1966. And I mean, to reproduce the exact exchange would involve reproducing the whole context, which would take more time. But substantially, what he said to me is that physics per se has no dignity and authority. Its dignity and authority comes from human factors, not physics. And for our purposes here, from human factors, not mathematics. That, as Lynn expounds, actually, in a three-part paper, which I sent out with the invitation to this class. The second part of that paper begins by a discussion of what is science. And there's a lot of other elements which I may not be able to put in now, but putting it down to the level of the individual scientist, he's a scientist because he's engaged in a critical re-examination of his own ideas, a critical re-examination of his own thinking. This is what science is. This is what science has always been. It's not math. It's not any of these things. It's not the dogmas they teach you in all the different graduate schools. It's a critical, creative, critical re-examination of the ideas of the scientist. And that's the same thing, if you think about it, as a critical re-examination of the history of science. And this is the distinctly human function. I mean, machines can't think. Artificial intelligence is bunk. And you can make a claim that animals can think, or some animals, depends what you mean by thinking. But no animal can do what the scientist does to make a scientific discovery, which is take his own thinking as if it was something outside of him, as if it was objects in nature or somebody else's thinking. Take his own thinking and examine it critically. Clearly, no animal could do that, as we know, because that relies on ideas, the person's objectification of his own thought process in order to examine it, which is at the same time examining the history of science, going back to say, we believed this in the past, but now there's a contradiction. It doesn't work. Why did we believe it? What evidence made us accept it? Where did we go wrong? How can we look at it differently? This is what every creative scientist has done. I mean, very obviously, if you think of Einstein's thinking process all through the last years of the 19th century into the beginning of the 20th century, this is what he was doing. He was re-examining the ideas in the history of science, or in science as he studied it, when it had come to a dead end. What was the problem? Where did we go wrong? What did we get wrong? De Broglie, the same thing. Perhaps not as famous as Einstein, but a great physicist also, and a great historian of science for precisely these questions. There is no boundary line between science and the history of science. It's the same thing. It's one and the same thing. And I mean, similarly, you look at scientists whom I've studied, Louis Pasteur, same thing. Why did we believe this? Why did we believe, for instance, that microorganisms generate spontaneously in certain situations, abiogenesis? What made us believe it? What evidence was there ever for it? Why did we believe it? And then, I mean, the mathematics, people imagine, because they're taught this in graduate school, which is an abuse of teaching process. They're taught that Einstein's general relativity is a mathematical theory or mathematical construction. It's not at all. I mean, he had developed the theory and then went with his friend Mark Grossman to find the mathematics which could express the truth which Einstein had already developed without the mathematics. I mean, this information is available to you from numerous sources. the mathematics was used to clothe the theory which had already been developed as an idea without mathematics. The same is true of Kepler. If you look at Kepler's life, and beginning with his scientific career, and started with his Mystery of the Universe, or Mysterium Cosmographicum, he had the hypothesis of the solar system before the mathematics and before even the relevant, or the most clinching relevant data. The theory, the new discovery, was in the human content as I tried to cover it and look at Kepler's historical investigations in astronomy, which underlay his breakthrough. So that is fundamentally what I wanted to communicate. This is a totally different process from mathematics, and the graduates. This is, there are, as we discussed in the last class, and we'll discuss more tonight. There are green shoots rising up in science. There are green shoots rejecting reductionism, something we discussed last week. We'll discuss more, and rejecting this closely associated cult dogma that science is mathematics. There are green shoots challenging that, but by and by large, our science grads and post-grads are being brainwashed into sterility, and this has been going on for a long time, through the cult of mathematics as science, or science as mathematics, and the closely related dogmas of reductionism. So, given where we started the course, I thought perhaps we should start this session with considerations like that.
Yeah, I think that's important, and it also is quite relevant, even to today's political situation, because we've heard over and over again with respect to climate change, and also during the pandemic, the refrain, you have to follow the science, you have to follow the science. And the science dictated all kinds of completely irrational things, which are totally unscientific, and in some cases not even backed up by data. So this was not even science as mathematics. This was science as, I don't know, political dogma. And I think we're at an interesting opportunity we have an interesting opportunity today to raise awareness about this, because the credibility of the scientific priesthood has been called into question because of the way it's been pushed. I don't know if you have any thoughts on that.
Oh, of course. The credibility of the scientific priesthood has been called into question because it's lied repeatedly about COVID, and the results of that have spread into doubt about everything not only the medical, but the scientific priesthood says, or almost everything they say, which is really appropriate. Because it's not enough to produce so-called authoritative results from Mount Olympus. The thinking of the population has to be elevated and supercharged in the process of a new renaissance. Really, the MAGA revolution is the seed, or is part of a new renaissance. And it's not, it's centered in the United States, but it's not even just limited to the United States. This is going on worldwide. And the, I mean, in order to shape the policies of the country, the average person needs basic grasp of scientific principles, and nowhere is this more important than an economy. And ditto, because economy is for LaRouche and for us, as we said in the title of the show, the king of the sciences.
Yeah, I mean, just getting back to this whole idea, uh, that what people have come to realize, especially, in respect to, the more outlandish claims of science is such as, the climate change hoax, which is supposedly backed up by data and given statistical reports. I guess the most ridiculous thing was the report earlier last week that 2023 was the hottest year in 125,000 years,
Oh my God.
as if we had any reliable temperature data past, maybe 100 to 150 years ago. So, and of course, we had the whole thing about COVID, which now everybody, even Fauci, is admitting was not based on science at all, but based on, political things. Maybe it'd be useful to discuss, for example, walk through an example of this process that you're talking about. You mentioned Einstein, um, and I also had in mind, Planck on the question of the second law of
Very
thermodynamics.
important.
Yeah, and the questions of thermodynamics. You know,
I mean,
Planck.
tell viewers, I don't know if they know, but I mean, I think you tell them one thing is the importance of this question of the second law of thermodynamics, why it's so politically important.
Well, it's ironic. It's very politically important because it's something which is accepted almost universally today as a scientific theory. Some people know its name, and some people know or taught basically a sort of superficial version of it in high school, or maybe even, I think they teach it in even in elementary school and middle schools. That the tendency of the universe is always to go from states of higher order to lower order. Of course, in grade schools, they give an example of this by saying, well, it's like, how heat flows from hot to cold, or how, you clean up your room and you make it all orderly, and then everything ends up being disorderly over time. And that's a reflection of a scientific principle called the second law of thermodynamics. And the whole world is like that, that everything that appears to be orderly and functional and progressive turns out really to be an illusion. And it's actually the universe is tending towards ultimately what Lord Kelvin called heat death. Now, this was not a belief prior to, say, 1850, 1860 in that form. It was seeped in the debate between Leibniz and Newton on the question of the organization of the solar system, the physics of the solar system, where Leibniz was a opponent of Newton and a proponent of Kepler, and decried both Newton's version of the calculus, which turned out to have been a plagiarized, stolen version from Leibniz, who was actually the original inventor, but also Newton's concept of force and planetary motion. And Leibniz correctly pointed out in the correspondence between Leibniz and a man named Clarke, who was the apologist for Newton, that under Newton's theory, the universe would always be winding down, and God would have to wind it up like a clock periodically to keep it going. But with the development of heat-powered machines, this opened up a new area of science which was a science of thermodynamics, because now heat, for the first time, was becoming a power source under man's control. So there was not only a necessity, but a inquiry to try and understand how this works. Originally, people thought that heat was a fluid. They called it caloric, which flowed from bodies, which was contained in bodies and flowed in and out of bodies the way like water flows in and out of a pipe. But that got disproven through several example means that this couldn't be the case. So the question is, what is heat? And this was, you have to remember that this was long before anybody had discovered the existence of atoms or molecules or the atomic structure, although it had been hypothesized as far back as the Greeks that matter in the very small was made up of small atoms. I think the word atom is a Greek word.
Yeah.
So when you look at heat, especially, for example, in a case of a gas, the macroscopic characteristics of that gas are easy to relate to each other by mathematical formula. Temperature, pressure, for example, temperature, pressure, and volume, right? If you increase the pressure, the volume decreases, temperature increases. If you decrease the volume, the pressure decreases, the temperature decreases. So there's a very simple mathematical relationship between temperature, pressure, and volume, for example. But there's not a simple mathematical relationship as to why heat would always go from the hot to the cold. Why would it tend towards equilibrium? But this was the basis on which machines actually function. The way a heat engine works, if you're using heat into heating up a fluid, either a gas or a liquid, to drive a piston, you heat up the piston, heat up the gas or whatever your working fluid is, and it expands, it increases its volume, and it pushes the piston, thereby lowering its pressure and temperature. And you put a flywheel on the piston, and piston pushes back in by increasing it. And then, of course, you have to add more heat, because part of as Carnot had demonstrated, part of the energy of the gas gets used up in work, turning the flywheel. So this is, important scientific inquiry. But the question is, what's actually going on in the process of, say, a gas being heated and then transferring its heat, going from a heat source to a state of equilibrium. Now, and at the time, in the 1850s, the two main proponents of this theory, which became known as the second law of thermodynamics, was Rudolf Clausius and Lord Kelvin, who was a Brit. Clausius was a German. And they both would writing mathematical treatises on the question of thermodynamics, and came to the false conclusion that while in a closed system, there were two things that happened. One was the energy remained constant, and the second was that what they called entropy, what Clausius called entropy, always increased. And entropy, Clausius said, was a entity which meant order versus disorder. So in the case of uh, a gas which is um, uh, an ordered system, and then it tends towards equilibrium, it goes from an ordered system to disorder. As a simple example of that is, I think I've used many times, is you put ice cube into water, and into a hot cup of water or coffee or whatever, and the water gets the coffee gets cooler, and the ice cube gets warmer until they reach equilibrium. And I think the best way to think about that is that is to think about it not in terms of heat flows, but think about it in terms of potentials. So when you have something like an ice cube in a warm cup of coffee, you have a great potential for change. There's a lot of transformation that can occur. And that's also the case in a heat engine, where you have you heat up a fluid, and then you have a chamber that is cooler, and the heat going in from the hotter to the cooler can do work, can push the piston. So there's a great potential for change. But once it gets into a state of equilibrium, it has to be wound up again in order to make it function. You have to put some kind of effort into it in order to get another potential for change, because that's how you do work. You can't do work in a state of equilibrium. And but they generalize this into a universal theory and hypothesize that, well, this was a law of the universe without any real basis to say that. So this and many other experimental efforts which took place at that time caused a great rethinking the process you were describing. What is a scientific theory? And Max Planck was the guy who really worked out for the first time the concept of real rigorous thermodynamics. And he started this by saying, well, what are we assuming here? Okay, what do we mean by a gas? And is this a fluid that is one thing? Like in the case of the macroscopic relations between volume, pressure, and temperature, we think of the gas as a single thing. But, or is this single thing really the effect of a large number, very, very large number of smaller things, of atoms or molecules or so forth, which are all bouncing around and moving around inside this whatever chamber it's in, so that are we dealing with a single thing, the gas, say, in a chamber, or are we dealing with a collection of billions of things, a large number of things? Well, if we're dealing with a single thing, then it's very easy to treat this in a mathematical way, or you can draw these mathematical relations. But if it's a collection of billions of things or trillions of things, like atoms, well, there's no possible way you could know or measure or count all the movements of all these little particles, what their trajectories are, how they interact, how they bounce against each other, and so on and so forth. So by assuming that the function of heat is the result of discreteness, that is a collection of billions of things, you're forced to rely on a mere statistics and probabilities to explain why it is that heat always tends towards equilibrium. An organized system always goes towards equilibrium. or goes from a state of great potential for change to a state of decreasing potential for change, or as Clausius would say, increasing entropy. And this is the way, so what Planck did was he took a very rigorous approach on this question and said, what are the assumptions that are going into our idea that the second law of thermodynamics is a universal law? Now, he believed that the second law of thermodynamics was a necessary consequence not of mathematics, but of a physical property that if you had, if you could have heat flow from cold to hot, then it would be possible to create a perpetual motion machine. You could create a heat engine, the equivalent of a pendulum which swings up to its maximum height and then swings down to its minimum height and swings up not just back to its maximum height, but higher. And you would get a perpetual motion machine, something which would create something out of nothing. And Leibniz said that can't happen, and he argued against that for perpetual motion. And Planck used the same kind of argument to say, well, it's reasonable to expect that in closed systems, you would have heat flow towards equilibrium. You would have an increase in entropy. But when you're trying to make a scientific, get a scientific understanding of this, you're really bound by the fact that you're making an assumption by making the assumption that the behavior of the gas is a function of billions of particles interacting with each other. Then you are forced into accepting that the behavior of these particles is fundamentally probabilistic, and therefore the greatest probability is equilibrium. You have a higher probability for that things go to equilibrium rather than disequilibrium. Now, what does that say about the universe? Might be kind of difficult for people to follow this, but let me bring it back to this point. What is the meaning of this for the universe? Well, and for economics. Well, when you look at the universe itself, look at the Earth, and you see that the Earth is not going towards equilibrium, it's going towards disequilibrium. You have life everywhere, and life goes exactly the opposite way towards from equilibrium towards equilibrium. It goes towards disequilibrium. It goes towards higher degrees of order. You know, the trees take in matter from the soil and energy from the sun through the leaves, and it organizes this disorganized matter into a highly organized system, which is the living process of the tree. And animals and other organisms do the same thing. So if it's more probable for things to be in a state of equilibrium, then life is the most improbable thing that could happen. And you ask yourself, well, how would life happen? Planck looked at it a completely different way and says, no, it's not that the second law of thermodynamics is the most probable thing that'll happen, but it's simply a reflection of a higher principle that the universe is tending towards higher states of organization and existence. I'm not sure that really clearly says what I was trying to say, Tony, but maybe.
Can you go just amplify on what you just said now, which I understood to say Planck said the second law exemplifies the universe going toward higher states of existence.
No, well, what he said is that the second law of thermodynamics is necessary only because it without it, you would be able to create a perpetual motion machine, a heat engine that produces more energy than it begins with. And that Leibniz already ruled out perpetual motion from the standpoint that if there was perpetual motion, something would happen in the universe which man couldn't understand, which would be unreasonable. And Leibniz believed in the principle of sufficient reason, that God did not create the universe in a way that would be irrational to the human mind. God created the universe in such a way there's a lot of things the human mind doesn't understand, a lot of things that are not knowable right now, but they're all things that can become knowable. And they can become knowable by man creating new concepts, both of science and nature, that allow man to understand the intricacies and the principles of God's creation. And that really is the fundamental principle of economics. Maybe I can illustrate this again with another example from one of Gauss's predecessors, Carl Gauss. This is a little bit in the domain of mathematics, but I think it's a simple example which illustrates things very clearly. I've used it before and it's very famous. But everybody learns in Euclidean geometry in elementary school or maybe middle school that that you have such a thing as parallel lines. That if you have a line that and a point that's not on the line, there's one and only one line which goes through that point, which, if extended to for as long as possible, will never meet the original line. That is, these are parallel lines. This is not proven. It's simply an axiom. It's sometimes called the fifth postulate. It's sometimes called the 11th axiom of Euclid and so forth. And it's accepted because it seems intuitively correct. But what Gauss pointed out was that this is an underlying assumption that is not stated in accepting this axiom. And that is that the surface in which these lines exist is flat. Because if the surface were curved, like in the case of a sphere, you could have two lines, like two lines of longitude intersecting the equator, and these lines would be parallel. But if they were extended as far as possible, they would ultimately meet at the North Pole. So there's an underlying assumption which is not stated in the axiom. And how can you determine, Gauss asked, how can you determine whether or not that axiom is true or not? And Gauss polemicized very strongly, mostly in private, that you cannot determine this except in the domain of mathematics. You can only determine this going outside the domain of mathematics and actually conducting measurements and experiments to determine whether or not the surface on which you're measuring things is flat or curved. If it's curved, there's a different mathematics that applies than if it's flat. But whether it's curved or flat cannot be determined by mathematics, but can only be determined by actually physically going out and measuring and doing things. And that, I think, is a very important lesson for people to get out from under this idea that mathematics is science. That science is actually questioning the assumptions you're making, and that, as you pointed out, it's as Lynn said, science is questioning whether or not you're questioning your own thinking. and asking yourself, is there a discrepancy between the way I'm thinking the world works and the way my interaction with the world tells me it's working? And if there's a discrepancy, then you got to ask yourself, what is the cause of that discrepancy? What is it that I don't know? And that's really what science is, and that's how economics progresses from lower states to higher states.
You want to draw more conclusions vis-a-vis economics in the second law? I mean, it's also, I mean, you gave me a very good explanation of the second law last night, but on randomness and the assumption of discreteness, which is very interesting.
Yeah, well, that's, I think, what I was trying to say, that, if you assume that your system, let's take a case of a gas, is the result of random interactions, is discrete, is made up of discrete individual interactions between atoms or molecules, then you are forced to accept the idea that these interactions are fundamentally random, that you cannot determine the trajectories. Theoretically, if you had super intelligence, you could measure every collision, and if you knew the initial conditions of every collision and the velocities and the direction of every collision, the momentum, that you could do a super calculation. And this is the real problem with reductionism, that somehow if you know the initial conditions and you have the right mathematical formula, then you can predict everything that will happen as a result of those initial conditions. Everything will be predetermined. And that assumes that each individual action is either completely determined, and since you can't calculate that, you say, well, then each individual action is independent of every other individual action, and therefore it's fundamentally random, and the only thing you can do is rely on the laws of mathematical laws of probability to measure or to estimate that the most probable thing is going to happen. And in the case of a gas dynamics, it's that the entropy will increase. Now, people apply this to economics, and they say, well, economics is fundamentally the individual decisions of the 8 billion people on the planet, or the 50 million people in the United States, or whatever economic population you're defining, and that each one of these atoms, i.e. individuals, is determining their actions based on their own individual wants and needs, desires, estimations, intentions, et cetera, and so they're all interacting as if they were particles in a gas that were randomly jiggling around and ending up producing some large-scale action. Now, the point is, if you assume that that's the basis of economics, then you're going to be led inextricably to the idea that economics is somehow a steady state, is headed towards equilibrium, that the most perfect economy is the one that maintains an equilibrium balance between all the economic interactions that are going on in the economy. But that's not what the economy does. What happens in economic activity is that there's a collaborative effort among peoples to interact with each other, not just contemporaneously, not just with their contemporaries, but also with previous generations and with an eye towards the future, most importantly. And as a result of that activity, mankind has over time, over our development, increased, have been in this constant state not only of non-equilibrium, but a state which is directed towards higher states of economic organization and activity. LaRouche measured this by the idea of potential relative population density. That is the amount of population that can be sustained on a given area of land relative to the characteristics of that land and the technology available to it. So it's not the population that currently exists or the population density that currently exists, but the potential to increase that potential relative population density. So that right there is not a random probabilistic interaction. There's an actual intention. And as Lynn pointed out, that intention is really the intention of human beings to carry out their actual human potential. And that human potential is not based on random interactions, but is based on an individual's relationship to society, to history, to the past, but most importantly to the future. Because human beings are the only creature that we know of. Actually, we don't really know this for sure, but I think it's true. Is definitely, we could take out the word only if you want to be a stickler, but human beings know our mortality. Every human being knows it's going to die, and it knows that the world is going to continue beyond its death. And the question that people ponder is what happens to me as an individual beyond death. So there's a curious paradox there that we have to live for what we are while we're alive, with our eye always on what happens after we're gone. And that then becomes a defining characteristic, in my view, and I think Lynn's, of how an economy develops. Why are we having this, how do we organize our economy today? People hear this all the time, so that the potential for our children, our grandchildren, our great-grandchildren, our progeny that we will never even know can have a greater power in and over nature than we do. So we conduct ourselves in that way. And when we lose sight of that, you end up with the kind of economic disorder that we have right now. So the idea of entropy, increasing entropy being a characteristic of the economy is an illusion, is a consequence of a misunderstanding of our own nature, our misunderstanding of man, and a misunderstanding that the creative power of man is fundamentally the ability to bring into the world something completely new, and to, in that way, create a potential that did not exist before we brought it into the world.
Yeah, that's terrific. And it's true. And the imagination of man is a cause, a powerful force in nature.
Exactly. I mean, one of these biologists who seems to be, or physicist who seems to be, you mentioned green shoots, a woman named Sarah Walker, who's been working with Lee Cronin on this question of assembly theory, put it in a very interesting way. When did rockets come into existence? Mankind had the idea of rockets and space travel 100 years before the first rocket ever left the Earth and got into space. So when did the rocket come into existence? It came into existence in the imagination of the early thinkers who conceived of the idea of going into space. Now, what was the practical purpose of going into space in their imagination? There could not have been, there was no practical purpose of going into space. We now know many practical purposes of going into space. But if you were a visionary uh, uh, in the late 1700s or early 1800s, and thinking about the power of the new power of heat powered machines, and you came up with the idea, well, if we could harness this power and create a vehicle that could have enough power to overcome gravity, to get out of the Earth's gravity and go into space, there's no practical reason for doing that other than the passion which one feels even imagining what it must have been like. You say, why would we do this? So that we can, to prove that we can, to do something that changes man's relationship to the universe completely in a way that it has never been able to be done before. So when did the physical rocket come into existence? It came into existence in the imagination. And the imagination is what drives the economy. And if you stifle imagination, as we've been doing pretty much since the end of World War II, increasingly, but especially in the last 40 years, 50 years, there's been an increasing effort to stifle imagination or to misdirect it into banal, ridiculous popular culture or something like that. Fantasy as opposed to actual imagination. You prevent that kind of new ideas and inventiveness from coming into existence. And I think this is one of the real evils in artificial intelligence. It's not merely, I mean, it's not merely the financial fraud that's going on, pumping up this idea that, artificial intelligence is going to be the next big business opportunity, but that by directing people or convincing people that machines are ultimately going to be able to think better than they do, you're destroying, you're trying to intimidate people from being imaginative. You're trying to crush people's imaginations. And by sitting there interacting with ChatGPT or something like that, you're destroying your imagination. Now, the fact is, you can use, advanced computer control systems and computer programming to control machines, but there's a human being who's doing the controlling. There's nothing in any machine that wasn't put there by a human being. So the machines are not going to take over mankind. But to tell people that is to try and convince them that the machine, that they are nothing different than the machine, and therefore they can be controlled by a machine which has more electricity going into it than your machine. I think you made the point, and I watched a video by this other physicist, Jeremy England, today, who made it in a weaker way, that this is a form of false idolatry.
Yeah, can I quote
Yeah,
Psalm
please.
15? I mean,
Yes.
I agree completely. It's idolatry. So, Psalm 15, Psalm 115, I'm sorry, people may know. It says, among other things, beginning with line 5, it says, they have mouths, but they speak not. Eyes have they, but they see not. They have ears, but they hear not. Noses have they, but they smell not. They have hands, but they handle not. Feet have they, but they walk not. Neither speak they through their throat. They that make them are like unto them. So is every one that trusteth in them.
I mean, that's as true today with respect to these machines as it is to the warnings of that the psalmist was trying to make to the pagan cults that were dominating uh, the region at the and when it was written. And that's what you're dealing with. It's a form of mass social control.
Tremendous. So maybe we can open up to our viewers here on Zoom who
Sure.
want to speak now.